Hello, this is Dr. Liu. In this video, we'll explain how to do dimensional analysis. So what exactly is dimensional analysis? Well, it doesn't have to be exactly dimensions or lengths, right? Lengths, areas, or volumes. The word dimension, it just means a generic unit or unit analysis, although we don't call it that way. So let me give you an example of what is a dimension and what exactly is a unit. So let's go with a meter, 1 meter. Okay, so the meter is a unit. All right, this is a unit. And what is the dimension of a meter? The dimension is length. Right? It doesn't matter which unit you're describing your length, it is a length. You can describe your unit, your length in miles, in feet, in inches, or in meters, in whatever other units. They're all length units, right? So dimensionality wise, it's called length, and we use this square bracket and a capital L for length. We also have other units such as mass, so say 1 kilogram. So this kilogram is a unit, right? And the dimensionality is called mass. So dimension is mass. So we use the square bracket capital M to represent mass. And another unit is a second. We use a second. Maybe 4 hours and maybe 3 days, right? These are all time units, right? So dimensionality is time. So we'll use a square bracket capital T for that. And we can also add another unit for current, for example, ampere. The dimensionality is current. Although it's not a fundamental dimension, it's basically the number of charges per time. So this will be some sort of charge per time that passes through a circuit. That is the current. The more charges per second is higher current, right? So in here we have the meter, the kilogram, seconds, and amp. This is our MKSA, or the system international, international unit system. All these fundamental units that we're using in introductory physics 1 for the first 3, and introductory physics 2 also uses current. All the other units are composite over all these fundamental units. Their dimensionalities are based on all these. So let's get started with what we can do with dimensional analysis, such as this composite unit of meters per second. So we know this is for speed or velocity. And meters per second, meters is a length. So dimensionally, meters is a length. Second is a time. So we have length over time unit. And if we look at a different unit, miles per hour. Okay, miles is a length unit. And hour is a time unit, right? So we also end up with length over time. So this means these two, although they're not, let's try drawing these two. Although they're not exactly equal to each other, they can be converted into each other because they have the same dimensionality. So you can convert a certain amount of miles per hour into another amount of meters per second. You can even add them together if you want. As long as you convert them into a common unit, you can numerically add the values, right? Say if your speed is 66 miles per hour plus maybe 5 meters per second, because you're walking along a train car, and the train car is moving at 66 miles per hour. You're walking, well, not walking, you're probably running at 5 meters per second. So you add them together, and as long as you convert both numbers into the same units, you can add them together. So this brings me a very important question is how important it is to analyze dimensionalities is very important, because before you add things together, you want to make sure they have the same dimensions. You cannot add speed with length. You cannot add apple with volume, right? So dimensionally, they have to be exactly the same in order to be added or subtracted. And that also applies to equations, which is a bunch of numbers or expressions being added or equated, right? So let's take a look at an example of an equation. So here we have an equation. It spells x equals x0 plus v0t plus 1/2 a t squared. And let's say that x and x0, these are in meters. So they are length units. They have length dimensions. Their positions, by the way. And v has a unit of meter per second. So v is length per time. Meter and a second, length and time. And a, well, let's write down a's unit being meters per second per second. So first of all, how does this thing work? Well, it works from left to right. So meter divided by second, and the result divided by second again. Right. So this has a dimensionality of meters length, and divide by seconds time, and divide by another second, another time. If you're a bit confused, that's how you divide, and then you divide later. Okay, and of course t has dimensionality of time, so t is time. So the goal here is to check whether this equation is dimensionally correct. That means, does it have the same exact dimension for all of the terms being added, right? If any one of the terms has a different unit than the other term, they cannot be added or subtracted. So this is a way to check whether a formula is invalid dimensionally speaking. Although you can never really check whether this 1/2 is correct, you can check whether the terms seem to be able to add, dimensionally speaking. So now let's do this. This x here is a unit of length, and that's equal to another x0, which is also unit of length. So far so good, right? So we have the same units being equated or subtracted, added. And then the unit of v0, velocity, length over time. Okay, so length over time, and then multiply by t, so times another time, which divides out the 1 over time. So we still have length. That looks good. Okay, so the last term, this is more complicated, and we can skip the 1/2 because it doesn't carry any unit. The a has this unit length over time, so length over time, over time. Then t squared has time squared, so the square of time divides out these in the denominator. That seems to be getting the lengths. So these divide out, and that divides out one of them, the other one divides out the other. Okay, so we end up getting a length is equal to a length plus a length plus a length. So all of them are the same exact dimensions. They can be added, subtracted, or equated. So this is a dimensionally correct equation. It says nothing about exact correctness because I could miss the 1/2, and dimensionally speaking, they're still the same. And I could mistake this with a negative, and dimensionally speaking, it's still the same exact dimensions. So this is just checking whether you say you missed the square, or maybe you square something that's not exactly a square in the formula. So you can check the dimensions to see if you can catch some errors. Okay, so let's have another example. V squared minus v0 squared equals 2at. So we're making the same exact assumptions of dimensionality as the previous question. So V would be this thing, the same as V0's dimensionality. So L over T, length over time squared. So we'll have length squared over time squared minus, that's the same exact dimensionality, length squared over time squared equals, skip the 2, A has length over time, so I can write this as length over the square of time, and then I have a T here and multiply by time. So doesn't look exactly the same as the left side. If you divide out this time with 1 over time, so you have length over time, and the left side of the equation has all the both terms, length over time squared, whole thing squared, right? So this is incorrect equation. Actually, the correct equation looks like this: v squared minus v0 squared equals 2ax minus x0. So now the x is a length times the a already has a length, so it becomes length squared, and a has 1 over time squared, so the result becomes length squared over time squared, just the same as the left side, right? So it's helpful to check units. And one last example, we have a formula that says F equals mv squared over r. So let's explain that F has a unit that looks like, well, this, kilogram meters per second squared. Alright, so what exactly is this unit? This is actually a force unit. How much force is required to, say, accelerate a kilogram mass at an acceleration of 1 meter per second squared? That's 1 Newton of force. So anyway, this one has a dimensionality of kilogram, which is the mass, and the meter, that's not mass, right? This is meter. Meter has length unit, and divided by second square, which is time unit squared. So that's the dimensionality of F. And we'll just assume that R has a dimensionality of length, just a length, radius, right? Okay, so let's work out the right hand side. The left hand side is already done. So the right hand side, we have m, which is mass. Let's put m here to explain. M is actually a mass quantity. So we'll have a mass quantity right here. And v squared, v is length over time. So length over time, and we square this whole thing, and then over a length. So we have mass and length squared over time squared. So length squared over time squared. There's also another length. So divide out one of the lengths. So now you have mass length over time squared. And the left hand side, this is the whole thing, is the left hand side. This whole force. So mass length over time squared. Mass length over time squared. So this is the same as the left hand side's dimensionality. This is actually equal to the left hand side. So dimensionally speaking, this is correct. And actually it is correct numerically, so the units or the factors are correct as well. Thanks.